institution which is affiliated to Anna University. This lecture is a part of a series on computational fluid dynamics and heat transfer. It is a lecture 2 in the lecture series on computational fluid dynamics and heat transfer. In this lecture 2, the reduced form of governing equations for the given fluid flow problem, discretization and finite difference solution of one-dimensional unsteady diffusion equations will be explained. Now in this August 5, 2026, I start to present the lecture 2 on the lecture series on computational fluid dynamics and heat transfer. In the lecture 1 itself, I explained the entire procedure of computational fluid dynamics and heat transfer, which I presented in the previous year, 2025. I think in the month of July I presented, where I explained that in this procedure, CFD-HT, which is an abbreviation of computational fluid dynamics and heat transfer, we arrive at the general equations governing the fluid dynamics and heat transfer from the basic principles of conservation of mass, conservation of momentum and conservation of energy. These general equations governing the fluid dynamics were arrived in the lecture 1. In this lecture 2, now I go for reducing this governing equation. That is, I am going to present a reduced form of the governing equations for the given fluid flow problem. And further, I am going to explain the discretization of the reduced form of governing equations for the given fluid flow problem in this lecture. In the previous lecture 1, I have arrived at these general conservation equations, governing equations, the continuity equation, which has been arrived from the conservation of mass principle, and the x momentum equation and y momentum equation. These equations were arrived from the conservation of momentum principles. Now I am going to reduce these governing equations for the given problem. The problem 1, which has been taken, is given below. The statement of the problem is: consider the problem of transient flow between infinite parallel plates with the boundary conditions u, which is the x component of velocity of the fluid flow, of 0t. 0 is the location where we find the velocity, and t is time, is equal to 0. U of 0t is equal to 0, and u of ht is equal to uppercase u. The initial condition is that u of y comma 0 is equal to 0. Here the kinematic viscosity of the fluid is 0.000217 meters square per second. The density of the fluid is 800 kilogram per meter cube. The velocity with which the upper plate is moving, that is uppercase u, is 40 meter per second. The distance between the plates, top plate and bottom plate, there are two parallel plates. One is top plate, another one is bottom plate. the distance, vertical distance between them is 4 centimeter. The problem is to use the FTCS scheme, that is, it is an explicit scheme: forward time, central space, scheme of finite difference with T max, maximum time period, is equal to 3 seconds, to compute the velocity within the domain for 3 different cases. For the first case, pressure gradient is 0, dP upon dx is 0. For the second case, the pressure gradient is positive, that is 20,000 Newton per meter square per meter. For the third case, the pressure gradient is negative, minus 30,000 Newton per meter square per meter. Use the option of computing time step using the stability criteria. So this is the problem statement. Here there are 2 plates, one is top plate, another one is bottom plate. And both of them are having length equal to infinity, width is equal to infinity, and the distance between the 2 plates, vertical distance between the 2 plates, is equal to small h, where L is length of the plate, W is width of the plate, h is vertical distance between the plates. Along the length direction we take the coordinate x, along the vertical distance direction we take the coordinate y, along the width direction we take the coordinate z. Thus the limits for x coordinate is varying from infinity to infinity, minus infinity to infinity, and the variation of y is from 0 to h, where 0 is the location of the plate, the bottom plate, h is the location of the top plate, that is the location of the fluid particle near the bottom plate, near the top plate. Z is also varying from minus infinity to plus infinity. So that is why it is called infinite parallel plates. The fluid flow is taking place in between these 2 plates. That is, the flow domain is such that it has infinite dimensions along the length and width directions. It has a finite dimension along the thickness direction, vertical distance direction, which is shown in 2-dimensional figure here. The bottom plate is shown here, where the boundary condition is 0. At any time, the x component of velocity of the fluid particle is 0, that is, the bottom plate is stationary. At any time, the x component of velocity of the fluid is upper case u, that is 40 meter per second, that is, the top plate is moving, bottom plate is stationary, which is shown by this symbol, and the top plate is moving with certain velocity, 40 meter per second. In between the bottom plate and the top plate, the thickness of the fluid which is flowing is 4 centimeter, h is 4 centimeter, where y varies from 0 at the bottom plate, y is equal to h at the top plate. The fluid has the kinematic viscosity. The fluid viscosity is given, which is the ratio of the dynamic viscosity and the density of the fluid. The density of the fluid is also given, which is 800 kg per meter cube. It is a constant density flow. Since rho is given equal to 800 kg per meter cube, which says that density is constant everywhere inside the domain. The x coordinate, y coordinate, z coordinates are shown here. Along the x coordinate, the component of velocity is small case u. Along the y coordinate, the component of velocity is small v. Along the z coordinate, the component of velocity is small w. What are the assumptions behind this flow problem First of all, it is an unsteady flow. How do you get this information? It is given in the statement itself. Consider the problem of transient flow. Transient means the flow behavior changes with respect to time. Transient. Steady means the flow behavior does not change with respect to time. It is not a steady flow, it is an unsteady flow, transient flow. Hence, the component of velocity u with respect to time, the component of velocity v with respect to time are not zero, they are not equal to zero. The density does not change with respect to time. The density changes with respect to time, is not equal to zero. But we have taken constant density flow, hence finally we will see that this density change with respect to time is also zero. It is a fully developed flow. That is another assumptions we make before solving this problem. What do you mean by that? Fully developed flow. The viscous effects are completely present over the entire flow domain. The effect of viscosity is felt everywhere within the flow. What do you mean by that? The velocity profiles do not change along the x-coordinate direction. That is, partial u upon partial x is equal to 0, partial v upon partial x is equal to 0. The flow is such that it is along the direction of the moving plate. The direction of the moving plate is x coordinate direction. So, the flow is also taken along the x coordinate direction. There is no flow along the y coordinate direction or z coordinate direction. The flow is created by the movement of the plate. If the plate, upper plate is stationary, there is no flow. The cause of the flow is the moving plate. If the moving plate velocity is 0, then there is no flow. In which direction the plate is moving? In x coordinate direction. Hence, the flow is also in x coordinate direction. There is no flow in y direction or z direction. That is why the arrow is given like this. We will also prove that why there is no flow in the y direction, why there is no flow in the z direction. Along the z direction there is no flow because it is an infinite plate. Along the y direction, why there is no flow, we will see in the following slides. As far as the fully developed flow condition is concerned, the velocity profile does not change along the x coordinate direction. Hence, the partial u upon partial x is equal to 0, partial v upon partial y x is also equal to 0. This is the snapshot of the flow at time t is equal to 0. During this time, if you see, the fluid is stagnant. How? As I told, the flow takes place due to the movement of the upper plate. At time t is equal to 0, the plate is stationary, upper plate is also stationary. Already I told bottom plate is stationary. At time t is equal to 0, the upper plate is also having 0 velocity. Hence, everywhere within the flow domain is having the limits varying from minus infinity to plus infinity along x direction, 0 to h along y direction, minus infinity to plus infinity along z direction. This is the flow domain. In the entire flow domain, velocity is 0. U, x component of velocity is 0 everywhere. At the bottom plate it is 0 because the bottom plate is stationary according to the no slip condition. At the top plate the fluid particle which is adhering or sticking to the top plate also having zero velocity, because the top plate is having zero velocity, not moving, u is equal to 0. Hence, everywhere within the fluid flow, velocity is 0, u is 0, u of y is equal to 0, y varies from 0 to high. This is the snapshot at time t is equal to 0 seconds. At time t greater than 0 seconds, at any time, the velocity profile will be like this, a linear profile. At the bottom plate, the velocity of the fluid is 0 because bottom plate is stationary due to no slip condition. At the top plate, the velocity is equal to the velocity of the plate, that is u, uppercase u, again due to no slip condition. In between the bottom plate and the top plate, the velocity varies linearly. This is the physics behind the velocity induced flow. This is called velocity induced flow or quiet flow. It is also called quiet flow. These are the governing equations which we arrived in the lecture 1 of the series: continuity equation, x momentum equation and y momentum equation. In this equations we find that partial rho upon partial t is equal to 0 because it is a constant density flow. Density is given as 800 kg per meter cube. So partial rho upon partial t is equal to 0. Rho is constant. Rho is equal to 800 kg per meter cube. Therefore, partial rho upon partial t is 0. Also, partial rho upon partial x is 0. Partial rho upon partial y is 0 because of this rho is equal to constant condition. Now, this continuity equation is expanded, that is, we differentiate the product partial rho u upon partial x is differentiated, rho partial u upon partial x plus u partial rho upon partial x plus, we expand this term, partial rho v upon partial y is expanded as follows: rho partial v upon partial y, v partial rho partial y is equal to 0. So, these two terms becomes the four terms in this equation, where these two terms are expanded, differentiated, and we obtain four number of terms. Already the first term is 0 because of the constant density condition. Now in this equation the second term is 0 because partial rho upon partial x is 0. The fourth term is also 0 because partial rho upon partial y is 0, again due to rho is equal to constant condition. What are the remaining two terms? Rho we have taken outside, partial u upon partial x plus partial v upon partial y, which is equal to 0. It's a product of two numbers, you see, rho multiplied by partial u upon partial x plus partial v upon partial y. If you make a product of these two numbers, we obtain the result is equal to 0. When will it happen? We know that rho is not equal to 0. One of the numbers, rho is not equal to 0. It is 800 kg per meter cube. So, which is equal to 0? If a product of two numbers is equal to 0, one of the numbers should be equal to 0. That is the second number, which is given by partial u upon partial x plus partial v upon partial y is equal to 0. So, this is the reduced form of the continuity equation. Initially, we have the continuity equation in this form, and now we have the reduced form of the given continuity equation. Partial u upon partial x is 0 because it is a fully developed flow. The flow is taking place along x direction. In a fully developed flow, the gradient of velocity along that flow direction will be 0. That is the physical concept for which another lecture has to be given, why such a physical condition is required. The partial u upon partial x is 0. Why partial u upon partial x is 0 in a fully developed flow? To explain this, another separate lecture will be given in this series in the future. Okay, the partial u upon partial x is 0 because of that condition, fully developed flow, that is viscous effect is prevalent over the entire flow field or entire flow domain. Hence, from the reduced form of the continuity equation, we obtain partial v upon partial y is equal to 0. What is the meaning of this? If we differentiate a function v, small v, which is the y component of velocity of the fluid flow with respect to y, that will be equal to 0. Hence, that function is not a function of y. The function will be a function of other than y variable. That is, the function v may be a function of x. Of course, it cannot be a function of z because already we have seen that the flow is in the xy plane. There is no flow along the z direction because of the infinite boundary conditions. Length of the plate is infinite, width of the plate is infinite. Hence, the two possibilities for the y component of velocity v is that either it is equal to a function of x or is equal to constant. These are the two possibilities if it is not a function of y. Partial v upon partial x is 0 because it is a fully developed flow. Any component of velocity, if you differentiate with respect to x, it will be 0 because velocity profile does not change in a fully developed flow. Already we have seen that partial v upon partial x is 0. Now we see that partial v upon partial x is also 0 because of that fully developed flow condition. Again, it is giving a meaning that viscous effect is present everywhere within the fluid flow. Hence, v is also not a function of x. Initially we told that v may be a function of x, but based on this fully developed flow condition, v is not a function of x. So, what is the remaining possibility? V is equal to constant. That is only the possibility based on the given conditions. Based on the fully developed flow condition, v is equal to constant in the flow domain, x which varies from minus infinity to plus infinity, y varies from 0 to h, z varies from minus infinity to plus infinity. So, this continuity equation, the general continuity equation is now reduced to this form: partial u upon partial x plus partial v upon partial y is equal to 0, and we have obtained a condition that v is equal to constant in the flow domain. Now we shall take up the other two equations. One is x momentum equation and y momentum equation. In the x momentum equation, the partial u upon partial x is 0, again due to the fully developed flow condition, and the sum of partial u upon partial x plus partial v upon partial y is equal to 0, again due to the reduced form of the continuity equation. The reduced form of the continuity equation says that partial u upon partial x plus partial v upon partial y is equal to 0. So these two terms, the second term in the left hand side and the last term in the right hand side, are equal to 0 based on the two conditions. The second term in the left hand side is 0 because of the fully developed flow condition. The last term on the right hand side is 0 because of the continuity equation, reduced form of the continuity equation. and this partial square u upon partial x square is also 0. That is, third term on the right hand side is also 0 because partial u upon partial x is 0. Once again, if you differentiate this partial u upon partial x, you will obtain partial square u upon partial x square, which is again 0. If you differentiate a quantity which is 0, that is also will be 0. So that is what explained here. There is no gravitational flow. There is no gravitational flow. The flow does not take place due to the action of gravity. The flow takes place only due to the movement of the top plate. So the force due to gravity, Gx is equal to 0, Gy is equal to 0. Hence, rho Gx is equal to 0, rho Gy is equal to 0. There is no force due to the gravity. So the first term on the right hand sides of both x momentum equation and y momentum equation are 0. Due to the fully developed flow condition, partial u upon partial x is 0. Hence, partial square u upon partial x square is also 0. Hence, the product of mu partial square u upon partial x square is equal to 0 as given here. The second term on the left hand side and third term on the right hand side of the first equation is 0. From the continuity equation, we have partial u upon partial x plus partial v upon partial y is equal to 0. That is, the last term on the first equation in the right hand side of the first equation is 0 based on continuity equation. Both the top plate and bottom plates are impermeable. Impermeable. What do you mean by that? The fluid cannot enter into the plates. Impermeability. Due to the impermeability condition, the velocity of the fluid flow, velocity component of the fluid flow is 0 along y direction. Both at the bottom plate location where y is equal to 0 and the top plate location y is equal to h. V is equal to 0 at both y is equal to 0 and y is equal to h. Y is equal to 0 is the location of the bottom plate where the fluid particle is adhering to the plate. Y is equal to h is the location of the fluid particle nearer to the top plate. In both these locations, the y component of velocity is 0. Already we have seen by simplifying or reducing the continuity equation, we have come to the conclusion that y component of velocity is constant everywhere within the flow domain. V is equal to constant. Y component of the velocity is constant everywhere within the flow domain. If it is constant everywhere within the flow domain, it should be equal to 0 because the flow domain also includes y is equal to 0 and y is equal to h. Here you see y varies from 0 to h. Either y is equal to 0 or greater than 0 or lesser than h or equal to h. That is the flow domain coordinate for y. At y is equal to 0, velocity is 0. At y is equal to h, velocity is 0. And velocity is also constant. Hence, everywhere it should be equal to 0. The y component of velocity is 0 everywhere within the flow domain. Not only at y is equal to 0 or y is equal to h, based on the continuity equation, it is also 0 in between the top plate and the bottom plate. That is, at all locations of the fluid flow between the top plate and bottom plate, the y component of velocity is 0. Therefore, the product, which is the second term on the left hand side, third term on the left hand side, rho v multiplied by partial u upon partial y is equal to 0 because v is equal to 0. Partial u upon partial y is not equal to 0. Which is 0? V is 0. If you multiply a 0 quantity with a non-zero quantity, the product will be 0. Hence, the third term on the left hand side of the x momentum equation is 0, because v is equal to 0. Based on this, if you see the x momentum of equation, the first term is not equal to 0, partial u upon partial t is not equal to 0, second term is 0, third term is 0 on the left hand side. On the right hand side, first term is 0, second term is not 0, third term is 0, fourth term is not 0, the fifth term and sixth term are 0. Hence, the x momentum of equation will become like this after the simplification. On the left hand side, the remaining term is rho partial u upon partial t. On the right hand side, partial p upon partial x plus mu partial square u upon partial y square. That is, in the x momentum equation, on the left hand side only one term is remaining, which is not equal to 0. On the right hand side, there are two terms which are not equal to 0, minus partial p upon partial x and partial square u upon partial y square. So this is the reduced form of the x momentum equation for the given fluid flow problem. The given fluid flow problem is the fluid flow between two infinite plates, where one of the plate is stationary, another plate is moving with a finite velocity. We will come to the y momentum equation. In the y momentum equation, all the terms in the y momentum equation are 0 except partial p upon partial y. Can you able to guess what is the reason? In the y momentum equation, if you see, the first term is partial v upon partial t. What about partial v upon partial t? If v is equal to 0, that will be 0. Since v is equal to 0, the differentiation of that 0 will be 0, either with respect to time or with respect to space coordinate x or space coordinate y. So all the quantities are 0, all the terms are 0 except the second term on the right hand side. Since v is equal to 0, partial v upon partial t is 0, partial v upon partial x is 0. In this term, v is also 0, partial v upon partial y is also 0. Since partial v upon partial x is 0, partial square v upon partial x square is 0. Since partial v upon partial y is 0, partial square v upon partial y square is also 0. Again, this term is 0 because of the continuity condition. Partial u upon partial x plus partial v upon partial y is equal to 0 from the reduced form of the continuity equation. So the only remaining term which is present on the right hand side of the y momentum equation is a non-zero term, is minus partial p upon partial y, pressure gradient along the y direction. So all the terms in the y momentum equation are 0 except partial v upon partial y. So in the y momentum equation, we have only one term which is non-zero, hence partial p upon partial y is 0. That is the condition we obtained from the reduced form of the governing equations. So these two are the reduced form of the momentum equations, x momentum equation and y momentum equation for the given fluid flow problem. So in this lecture, first the part of this lecture is completed, which is about reduced form of the general governing equations for the given fluid flow problem. Reduced form of the continuity equation is this: partial u upon partial x plus partial v upon partial y is equal to 0. Reduced form of the x momentum equation is given here. Reduced form of the y momentum equation is given here. Next part of this lecture is discretization of the reduced form of the governing equation. What is discretization? In a computational fluid dynamics and heat transfer procedure, the partial derivatives in the governing equations of fluid dynamics and heat transfer are replaced with the algebraic difference coefficients. This process is known as discretization. If you see in this continuity equation, reduced form of the continuity equation, these partial differential quantities, which are the partial differential quantities? Partial u upon partial x is a partial differential quantity. Partial v upon partial y is a partial differential quantity. These two quantities have to be replaced with algebraic quotients. What do you mean by algebraic quotients? That I shall explain in the further slides. So this procedure is called discretization. The partial derivatives, partial differential quantities are replaced with algebraic difference coefficients. So in the entire procedure of CFD-HT, we have completed the general equations governing the fluid dynamics and heat transfer in the lecture 1 of this series. In the first part of this lecture 2, reduced form of the governing equations for the given fluid dynamics has been demonstrated. Similarly, we can demonstrate for a heat transfer problem. Here we have demonstrated for a fluid dynamics problem which involved a fluid flow. That is a fluid flow between two plates which are infinite in size, in length and width directions, where one of the plate is stationary, another plate is moving. For this kind of the given fluid flow problem, we have reduced the governing equations to simplified. We simplified the governing equations. The next step is discretization of this reduced form of the governing equations for the given fluid dynamics problem or heat transfer problem. Before going into this, first I am going to explain what is discretization. There are various discretization methods. One is finite difference method, another one is finite volume method or finite element method. In each of these methods we have two subtypes. One is explicit method, another one is implicit method. Each method involves an analysis called stability analysis to test the convergence of the solution. Algebraic finite difference representation of partial derivatives are based on Taylor series expansion. As I got told, the partial derivatives, partial differential quantities in the reduced form of the governing equations have to be replaced with finite difference coefficients. How do you arrive at this? That is algebraic finite difference coefficients. How do you arrive at these algebraic finite difference coefficients? Based on the Taylor series expansion procedure. For a function of f with respect to x, the value of the function at x plus delta x point can be obtained using the value of the function at point x and the derivatives of this function. That is, first derivative of this function partial f upon partial x, partial square f upon partial x square, etc. for nth order differential of the function up to the nth order of the differential function. Using these values of the functions f and partial differentials of various orders, we can find the value of the function at x plus delta x location. So this is the equation 1, which is the fundamental for the algebraic finite difference representation of the partial derivatives. This equation 1 is called Taylor series expansion. I am going to explain the discretization process using a function f of x is equal to sine 2 pi x. It is an example function I have taken. The aim is to find f of x plus delta x, that is the value of this function at a point x plus delta x using the various numbers of terms in the equation. If you use only the first term, what will be the value of the left hand side? If you use the first two terms on the right hand side and neglecting the remaining terms in the equation 1 on the right hand side, what will be the value of the left hand side? If you use the first three terms and neglecting all the terms from the fourth term and calculating the sum of these three terms, what will be the value of the left hand side? Like this, we take the various number of terms on the left hand side, right hand side of the first equation and find out the value of the left hand side in equation 1. That is the aim. Based on which we arrive at the accuracy of each and every in each and every case. Let x is equal to 0.2, that is the value of the function f at x is equal to 0.2 can be obtained from this equation by substituting x is equal to 0.2, and let us take delta x is 0.02, that is the differential distance from the location x is equal to 0.02. For this case, we draw the x-axis, and along the x-axis we have taken x is equal to 0.2, delta x is 0.02, so x plus delta x is 0.22, that is 0.2 plus 0.02, which is equal to 0.22. Along the y-axis we find the value of the function f of x using this function sine 2 pi x. We know this is the white line is the given function sine 2 pi x, that is the analytical function which we can obtain using this equation sine 2 pi x. If you substitute x is equal to 0.2, you will obtain the value of 0.9511. If you substitute 0.22 for x, you will obtain 0.9823. This is a simple function, but in computational fluid dynamics we have very complex functions for which we cannot calculate the value of y in this as we are doing in this example in a straightforward manner. Since it is a simple function, we are able to find out the value of y at various places by substituting for x 0.2, 0.22, etc. But in computational fluid dynamics, we don't have such a simplified function. We have a complex function for which we don't have any such simplified or exact function. We don't have such exact functions. It is an exact function, y is equal to sine 2 pi x. In computational fluid dynamics problem, we don't have such exact functions. We have inexact function, that is approximately equal to, y is approximately equal to some right hand side of the function. At that time, we have to go for numerical procedure to find out the approximate value of the y. So for which we go for discretization. What about the points given in red color 3 and 4, we will see now. So f of x is given as sine 2 pi x. If you differentiate f of x, what we obtain is partial f upon partial x, which is, if you differentiate sine function, you obtain cosine function, cosine of 2 pi x. Again you differentiate the factor which is within the parenthesis 2 pi x. If you differentiate 2 pi x, you obtain 2 pi. Hence the result of partial upon partial x is equal to 2 pi cos 2 pi x. Now I am going to use only the first term in the equation. What is the first term in this equation? F of x plus delta x. F of x plus delta x is approximately equal to f of x. Why we say approximately equal to f of x? Because we have omitted all other terms except the first term. We are using only the first term. We have neglected the second term. We have neglected the third term, fourth term, up to the nth term, infinite number of terms. We have neglected. We have taken only the first term in this expansion, series expansion. Hence, instead of this equal sign, we use approximate sign. F of x plus delta x is approximately equal to f of x, because we have neglected the terms from the second term on the right hand side. Okay, now x is equal to 0.2, delta x is equal to 0.2. So f of 0.2 plus 0.2 is approximately equal to f of 0.2, x is equal to 0.2. Substitute wherever x is there, substitute 0.2, wherever delta x is there, substitute 0.0. So this function, that is the value of the function at a subsequent position 0.22 is equal to the value of the function at 0.2. What is the value of function at 0.2? If you substitute x is equal to 0.2 in this equation, it is sine of 2 multiplied by pi multiplied by 0.2. If you do in calculator, you will get 0.9511. So what is f of x plus delta x? F of 0.2 plus 0.22, that is also equal to f of x. So we obtain 0.3, which is 0.9511. 0.3 is nothing but approximate value of the function f of x when you use the first term in the Taylor series to find the value of this function at x is equal to 0.2, which is an approximate value. You see what is the difference? The exact value is here. 0.2 is the exact value obtained from analytical solution, whereas 0.3 is an inexact value, approximate value obtained using numerical procedure, that is using Taylor series expansion, where we have neglected all the terms except the first term. What is the percentage error by following this procedure where we have used only the first term in equation 1, that is first term in Taylor series expansion? The exact value is 0.9823, which is the accurate value, whereas the obtained value is 0.9511. With respect to 0.9511, the percentage of the error is 3.2%. Okay, now we are going to use the first two terms in the equation 1. In this Taylor series expansion, we are going to use the first two terms on the right hand side, that is f of x term and second term partial f upon partial x into delta x term. Once again we calculate the f of x plus delta x using this f of x equal to sin 2 pi x, we obtain f of x value. Using 2 pi cos 2 pi x, we obtain partial f upon partial x. So we are using the first two terms. Wherever x is present, 0.2. Wherever delta x is present, use 0.02. We obtain f of 0.2 plus 0.02 is equal to sin 2 pi into 0.2 plus 2 pi cos 2 pi 0.2, 0.02 upon 1 factorial. We obtain 0.9899. What is the percentage error here? 0.9823 is the exact value. This is the approximate value which we have obtained. That with respect to the exact value, it is 0.771%. So that is the fourth point. So in the fourth point, we obtained 0.989. Initially we had 0.9511, which is far away from the exact value 0.9923. Now we have closely reached the 0.2. 0.9899 is nearby 0.9823 when compared with 0.9511. Now we use the first three terms in the equation. We use the first term we use the second term, we use the third term of the Taylor series. We neglect all of the terms from the fourth term on the right hand side of the first equation. That is Taylor series expansion equation. Once again we find f of x plus delta x using x is equal to 0.2 and delta x is equal to 0.2. F of x plus delta x is equal to f of x plus partial f upon partial x delta x plus partial square f upon partial x square at x delta x square upon 2f factorial. We obtain the value of partial f upon partial x 0.0388, partial square f upon partial x square 0.0075 minus 0.0075. If you substitute these two quantities here, we obtain f of 0.22 is 0.9824. Now you obtain the percentage error, which is 0.01 percentage. 0.9823 is the exact value, 0.9824 is the value which we obtain by using the first three terms on the right hand side of the Taylor series expansion, where we have neglected all other terms from the fourth term. We obtain such an approximate value. Now you see the value of the function is in between 0.4 and 0.2. It is nearby 0.2. So when the number of terms in the Taylor series expansion increases, the percentage error decreases. Initially the percentage error is 3.2 percentage, which has been reduced to 0.771 percentage when two number of terms are used. When three number of terms are used, again percentage error is reduced to 0.01 percentage. So when the number of terms in the Taylor series increases, when we use more and more number of terms on the right hand side of the Taylor series, when we use only one term, the error is more. When we use two number of terms, the error is small. When we use three number of terms, the error is further small. The error decreases when we use more and more number of terms on this right hand side of this equation. That is what saying. The accuracy of the solution increases. So one is the initial point, two is the subsequent point. Using the value of the function at initial point, we find the value of the function at the subsequent point. The white line is the exact solution, which is given by f of x is equal to sin 2 pi x. So at point 2 we have the exact value 0.9823, which we obtain from analytical function directly. When we use Taylor series expansion in the first guess, when we use the first term of the right hand side of the Taylor series, we obtain the 0.3, which is the first guess which has highest error. In the second guess, we obtain 0.9899, where we have used the first two terms on the right hand side of the Taylor series, where the error has been reduced. In this 0.4, we take into account the slope of the function. In the 0.5, we take into account the curvature of the function also, along with the slope of the function. Hence, the error is further reduced. The value of the approximate value, the approximate quantity, approaches the value of the exact quantity, where 5 is the point we obtain by considering the first three terms on the right hand side of the Taylor series. So this is the procedure of the concept of discretization. When we go for more and more number of terms on the right hand side of the Taylor series to approximate the left hand side function, the error decreases, the accuracy of the solution increases. Now we use this concept of the Taylor series for the given problem, numerical solution of the one-dimensional unsteady diffusion equation. Why it is called a one-dimensional problem? In this problem, the top plate is moving, the bottom plate is stationary. u is a function of only y. Velocity varies only along y direction. Hence, it is called a one-dimensional problem. Variation of the flow quantities takes place only in one direction. If the variation of the flow quantities takes place in two directions, then we call it as a two-dimensional problem. If the variation of the quantity takes place in three directions, then it is a three-dimensional problem. In a two-dimensional problem, u is not only a function of y but is also a function of x or z. In a three-dimensional problem, u is a function of x, y and z, all the three coordinates. It is a one-dimensional problem. It is an unsteady problem. For this unsteady problem and one-dimensional problem, we are going to arrive at the discretization of the reduced form of the governing equation. That is numerical solution of a one-dimensional unsteady diffusion equation. What is that diffusion equation? The x momentum equation, which we have arrived in the previous part of this lecture. The x momentum equation. Rho partial u upon partial t is equal to minus partial p upon partial x plus mu partial square u upon partial y square. Along the x axis, y is taken. Along the horizontal axis, y is taken. Along the vertical axis, u is taken. Smaller u, that is small case u, that is x component of velocity. The y is the distance along the thickness direction of the fluid film. The y varies from 0 at the bottom plate, y is equal to h at the top plate. So this variation of y is taken along horizontal direction, and the variation of the velocity u, here you see the velocity component u is 0 at the bottom plate, is maximum equal to the velocity of the top plate u, uppercase u, at the top plate location. There is a variation in the velocity. This variation, how it varies, is taken as the vertical direction. So this is the function. The line, curved line is shown as the variation of u along the y direction. We don't know how it varies. What I have shown there is a linear profile. Initially we assume it is a non-linear profile. Finally we will come to the conclusion that it is a linear profile. If it is the actual case is linear profile, we will come to that conclusion, or if it is a non-linear profile, we will also come to that conclusion. Before that, we initially assume it is a non-linear profile, where the value of u at I minus 1 point, where I is an index which varies from 1 to n. When y is equal to 0, y is the physical location of the fluid particle near the bottom plate. Y is equal to h is the physical location of the fluid particle near the top plate. So the bottom plate location is given by the index 1, the top plate location is given by the index n. In between, the index I varies from 1, 2, 3, etc., etc. I minus 1, I plus 1 up to uppercase n. So for each and every value of y, we have from the boundary in the domain limits y is equal to 0 and h, we can have a correspondence with the indexes. When y is equal to 0, it corresponds to index 1. When y is equal to h, it corresponds to index n. When y is equal to I, it corresponds to index I, etc. When y is equal to y minus delta y, it corresponds to I minus 1. When y is equal to y plus delta y, it corresponds to I plus 1. So for each and every value of the y of the physical location of the fluid particle in between the bottom plate and top plate, we can have a correspondence with the indices, index I from 1 to n. So when we have the boundary condition u is equal to 0 when y is equal to 0, you see the bottom plate is stationary, u is equal to 0 when y is equal to 0. What about the u at top plate? It is equal to uppercase u, 40 meter per second. So that is what given. When y is equal to 0, u is equal to 0, at y is equal to h, u is equal to 0. This form of boundary condition can be transformed into the boundary condition in terms of the index I, that is u is equal to 0, u1 is equal to 0, u is equal to 0, that is u subscript n is equal to 0, where I is the node or grid point or index. Ui is the velocity component in the x direction on the ith node. What is the velocity component on the first node? u1 is equal to 0. What is the velocity component on the nth node? That is equal to u. So ui is the component of velocity on the ith node, ui minus 1 is the component of velocity on the I minus 1th node, ui plus 1 is the component of velocity on the I plus 1th node with these two boundary conditions. Now this Taylor series expansion, which is given as f of x plus delta x is equal to f of x plus partial f upon partial x delta x by 1 factorial plus partial square f upon partial x square delta x square by 2 factorial plus etc. etc. This equation 1 is now rewritten in terms of node values, that is using the I plus 1, I minus 1 using equation 2. Instead of f of x plus delta x, here f is a function. Here which is the function in the given problem? U, x component of velocity, smaller case u. I told for every value of y, there is a corresponding value of the index I. Don't confuse, here I am using x, there I am using y, don't confuse. X is a variable. Here I am not meaning the x coordinate direction. X is a variable, generic variable. Here in the given problem it is equal to y. X is given as y, where y is the distance along the vertical direction between the bottom plate and top plate. So instead of y, I can say I using the index I. Instead of delta x, I can say x plus delta x is given by I plus 1 when it is the location x, where for the given problem it is the location y. Again, when you transform it into the node values, it is corresponding to I. Here it is x plus delta x, in the given problem it is y plus delta y. Again, when you make it corresponding to the grid number, it is I plus 1. So instead of wherever we have x, we use I, wherever we have delta x, we use the value of I plus 1 minus I minus 1, that is delta y What is the difference between I plus 1 and I minus 1? Delta y. So ui plus 1, which is equal to f of x plus delta x, ui which is equal to f of x. Next, partial f upon partial x. Instead of partial f upon partial x, we use partial u upon partial y. Here f is equal to u, equivalent to u. Here y is equivalent to x in the general Taylor series expansion. Again, instead of delta x, we use delta y. Here, delta x, generic variable in the Taylor series expansion. In the given problem, it is delta y by 1 factorial. Similarly, we can write the third term. Now, using this equation 2, now I arrive at the value of partial u upon partial y from the second term, which is equal to ui plus 1. When you bring this ui to the left hand side, it is ui plus 1 minus ui plus 1 minus ui. I divide by delta y because what the aim is to find out partial u upon partial y. And this third term on the right hand side, when it comes to the other side, it becomes minus partial square u upon partial y square, delta y square upon 2 factorial, 1 upon delta y, minus etc. etc. Now we find this gradient of the velocity, x component of velocity along y direction at a point I, grid point I, is a function of ui plus 1, ui partial square u, delta y, etc. Now if you see this equation, which is given as equation 3, this term is called finite difference approximation. What about the remaining? These are called truncation error. These are called a truncation error. Why we call it as truncation error? During the calculation of this differential quotient, this is called differential quotient, partial differential quotient. Quotient is the ratio between partial u and partial y, partial u upon partial y. In calculating this value, we use only this finite difference approximation. It is a finite difference approximation. Why it is called finite difference approximation? First of all, it is an approximation because we are going to neglect all the other terms which are under the truncation error. We are going to use only these two terms. And why it is called finite difference? ui plus 1 is a finite quantity, ui is also a finite quantity. The difference between these two finite quantities is a finite difference. Difference of the finite quantities. That is why it is called finite difference approximation. FDA. Truncation error is given by TE. So in equation 3, the truncation error contains the terms with the delta y to the power 1. If you see here delta y square, here delta y, when you cancel, you obtain delta y. So the delta y is having the power of 1, hence this equation is called first order accuracy equation. When delta y having a power of 1, it is called first order accuracy equation. Which is called first order equation? When we neglect all the terms containing the truncation error, when we use only the first two terms on the right hand side of this equation 3, we obtain an approximate equation for the partial differential coefficient, that is partial u upon partial y at ith node is approximately equal to ui plus 1 minus ui upon delta y. This is a first order accuracy equation. Equation 4 uses values of the u, that is the x component of velocity, to the right side of I. Is that this is the grid point I. At the grid point I, the velocity is ui. At the right side of the grid point I plus 1, the velocity is ui plus 1. So it uses the velocity of the fluid particle, that is x component of fluid particle, to the right side of the grid point I, that is in I plus 1, that is ui plus 1 and ui. It is using ui and ui plus 1. Hence equation 4 is known as a forward space finite difference approximation. First of all, it is an approximation equation. Why it is an approximation equation? Because neglected all the terms except the first two terms on the right hand side of the third equation. The collection of these terms, the sum of these terms which are neglected is called truncation error. Hence, we have the equation 4 which is an approximate equation by neglecting all these truncation error terms. Second, it is a finite difference equation because it has the finite difference quantities. We obtain the difference between these two finite quantities. That is why it is called finite difference approximation. Why it is called a forward space with respect to the spatial coordinate. With respect to the spatial coordinate, I is the grid point corresponding to the spatial coordinate y. I plus 1 is the grid point corresponding to the spatial coordinate y plus delta y, which is to the right side, of the grid point I. That is why it is called forward space. When we move along this y direction, when we move along the direction where it varies from 1, 2, 3, 4, etc. up to n, it is a forward direction. When we move along the other direction, that is from n to I plus 1, I minus 1, 3, 2, 1, it is a rearward difference. So, in this approximate equation, we have the terms of the u which contain I and I plus 1, that is to the right side of the grid point I. That is why it is called forward space. It is called forward space. It is a spatial quantity. Y is a spatial quantity. Y is the distance along the thickness of the fluid film in the vertical direction, vertical spatial direction. That is why it is called forward space finite difference approximation. Equation 4 is also known as a first order forward space finite difference approximation. Why it is called first order finite difference approximation? The delta y has a power 1 in the equation 3. The truncation error term has the maximum power of delta y is 1. That is why it is called first order forward space finite difference approximation. Now, writing the Taylor series expansion for ui minus 1. Here we have written the Taylor series expansion for ui plus 1, that is f of x plus delta x is equal to f of x plus partial f upon partial x delta x by 1 factorial plus partial square f upon partial x square delta x square by 2 factorial plus etc. as we have in the Taylor series expansion 1. Now we are going to find out f of x minus delta x. Wherever we have plus delta x, we substitute minus delta x. Here it will become minus delta x by 1 factorial. Here it will become minus delta x whole square by 2 factorial. When we make a square of a minus delta x, again it will be delta x minus delta x power n, etc. So wherever we have delta x, we use minus delta x, then we obtain the rearward difference. F of x minus delta x is ui minus 1, f of x is ui plus partial f upon partial x. Instead of plus delta x, we use minus delta y because it is f of x minus delta x plus partial square u upon partial y square. I told minus delta y whole square plus etc. This is equation 5. What is the product of these two quantities? One is a positive quantity, another one is a negative quantity. A net product is negative. What is the product of this quantity? It's a positive quantity. It's a square of negative quantity. Again, it is a positive quantity. So partial u upon partial y, once again we obtain from this equation, fifth equation, that is we bring this ui to the other side, we bring the other terms to the other side, keeping only partial u upon partial y in the left hand side. We obtain ui minus 1 by delta y plus partial square u upon partial y square delta y square by 2 factorial 1 upon delta y plus etc. etc. This equation is given as 6. The first two terms together is called finite difference approximation, FDA. The sum of the remaining terms is called truncation error, TE. When we truncate means we cut, we neglect all these terms in this equation except the first two terms. When we use all the terms in this equation, it is an equal quantity, it is an exact value of the function. When we neglect the number of terms on this, any number of terms on this exact equation, then we obtain an inexact quantity, which is an approximate quantity. Partial u upon partial y is now an inexact approximate quantity, which is ui minus 1 by delta y, which is given as equation 7. First of all, see, the equation 6 contains the truncation error with the delta y to the power 1. Delta y is having a power of 1. Hence, it is a first order accuracy approximation. Now again see the equation 7, it contains the value of u to the left side of I. It contains the value of u at left side of I. The value of u at I is ui. The value of u at I minus 1, which is to the left side of I. I told when you move from 1, 2, 3, 4, I minus 1, I plus 1, it is a forward direction. When you move from I plus 1, I minus 1, 3, 2, 1, it is a rearward direction. So we have the quantities of u which are to the left side in the rearward direction of I. That is, equation 7 contains the values of u to the left side of I is that it contains ui and ui minus 1. Hence, the equation is called a rearward space finite difference approximation. It is an approximation because we have neglected the various terms on the right hand side of equation 6. It is a finite difference quantity because it contains the difference between two finite quantities ui and ui minus 1. Finally, it is a rearward difference because it contains the value of u to the left side of I and the value of u at I. Hence, it is a rearward difference approximation, rearward in space difference approximation. Already we have seen that in this approximation we have the delta y having the power 1, hence it is also called a first order rearward space finite difference approximation. So like this, we have the discretization procedure where we have, in the first case, we have obtained the partial u upon partial y, that is the equation 4, which is a first order accuracy, forward space, finite difference approximation. The same partial u upon partial y at the ith grid point can also be written in this fashion, where it is called first order accurate rearward space finite difference approximation, shown here using equation 7. Now subtracting the equation 5 from equation 2. Now I am subtracting the equation 5 from which we have written using Taylor series expansion for ui minus 1 from equation 2, which we have written for the u using Taylor series expansion using I plus 1 term and I term. When we subtract the equation 5 from equation 2, what we obtain is ui plus 1 minus ui. The right hand side we have to manipulate, we have to do a lot of mathematical addition, subtraction, simplification. Finally, you obtain the equation like this. Now solve for partial u upon partial y again. we obtain the approximation like this. Here we have, see, the component of x component of velocity on both sides of the given grid point. Here what we are going to find out, the partial differential quantity, partial u upon partial y at ith grid point we are finding out. To find out the value of this differential quotient at ith grid point, we use the value of u both on the left hand side, that is ui minus 1, and on the right hand side ui plus 1. That is why it is called a central difference. Here again you see this the remaining terms are truncation error terms which have the power of 2. The truncation error terms, the maximum power of the truncation error term having delta y is 2. Hence it is a second order accurate solution. The lowest order of term in the truncation error involves delta y to the power 2. Hence the approximation given by equation 9 is a second order accurate solution. Again, the finite difference contains the values of u to the left hand side as well as right hand side of the given grid point I. Hence it is called a central difference, central space finite difference. Equation 9 uses the values of u on both sides of grid point I, is that it uses ui minus 1 and ui plus 1. Hence equation 9 is called a central space finite difference. Hence finally we say that equation 9 is a second order central space finite difference approximation. Now what we are going to do, we are going to add the equation 2 and equation 5. Initially what we have done, we have subtracted equation 5 from equation 2. What we obtained is a second order central space finite difference approximation. Now we are going to add both these equations, that is ui plus 1 and ui minus 1. After manipulation, after mathematical addition and subtraction and simplification, what we finally obtain is solving for partial square u upon partial y square at the grid point I. We obtain such a equation 10, where we see that the finite difference contains the value of u at ith grid point, the value of u at the left hand side of the ith grid point ui minus 1, the value of u at the right hand side of the ith grid point ui plus 1. If you see, the lowest power of delta y is 2 in the truncation error. Hence it is a second order accurate solution. It contains the values of u on both the sides of the grid point I. So it is also called a central space finite difference. The lowest order term in truncation error involves delta y to the power term power 2. Hence approximation given by equation 11 is the second order accurate solution. Equation 11 uses the values of u on both the sides of the grid point I. Hence approximation given by equation 11 is a central space finite difference. Hence equation 11 is also known as a second order central space for second difference approximation. Why it is called second difference approximation? It is the approximation of the quantity, partial differential quantity, partial square u upon partial y square. Whereas in the equation given here, it is partial u upon partial y. Ninth equation is partial u upon partial y. That is first difference. Whereas here it is a second difference, partial square u upon partial y square. With this, I conclude this lecture 2 on the series of the lectures on computational fluid dynamics and heat transfer. We have seen in this lecture the reduced form of the governing equations. In the lecture 1, we have arrived at the general form of the governing equations from the basic principles of conservation of mass, momentum and energy. Now by simplifying these general equations of continuity and momentum, I have arrived at the reduced form of the governing equations for the given fluid flow problem, where the given fluid flow problem involves a fluid flow between two parallel plates which are infinite in length and width. having the bottom plate stationary and the top plate moving. For this given problem, we have arrived at the reduced form of the governing equations of continuity and momentum. Now, after that, I have explained the concept of discretization, the procedure of discretization, from which we have arrived at the four different discretization equations, such as first order forward difference, finite difference approximation in space, first order rearward difference, rearward space, finite difference approximation, first order central difference, finite difference in space approximation, second order central space, finite difference approximation of first order accuracy and second order accuracy. In the next lecture of this series, I shall apply this discretization procedure for the given fluid flow problem, that is the flow between parallel plates. Thank you for your kind attention. Thank you.